Then after that, you try to fit it into where it goes or what output it goes, correct?
Yes, yes.
Yes. So the whole thing need to go smoothly. It is assumed to go smoothly. If it is not going smoothly, as you say, deviation, then you need to rectify.
Yes, yeah.
That's what you are asking, right, Fossil?
Yeah, yeah, yeah. I just didn't understand that particular
No,
word
this is
loss.
the
Yeah,
mapping he is giving. This is the whole
yeah,
mapping he is giving.
yeah.
This is the way it has to behave.
Mm-hmm.
This whole thing, a simple neural network, this
Mm-hmm.
is a behavior expected, as
Mm-hmm.
you say.
Understood.
This is a behavior expected. It has
Mm-hmm.
to supposed to go like this. It's not
Mm-hmm.
going like this. Then what to do? That's what
Understood.
he is saying. Am
Mm-hmm.
I correct, Peterson?
Yes, yes, yeah.
Yeah. Yes. Okay, you can go ahead.
Okay, sure. Yeah. So I will explain the loss again. Yeah, I will, but I want to, because it's a bit deep, so that's why I did not go one by one, because we'll get lost. So at first, I want to give the entire summary of what is happening. Then I will go into the depth. Yeah.
Thank you.
Okay. Yeah. So just, yeah, remember, first will be the data gathering stage. Next, we have to use the data, some of that data to do training. Then finally we use the remaining data to do testing. Okay. Yeah. So yeah, then during testing, okay, so the strength of neural networks as opposed to,
Sorry, Peterson, can I put some insight
sure,
whether it's
sure.
correct or not?
Okay.
Training is to make your model so you see that it is working. Testing is you put to the actual values. Am I correct?
Yes, so the actual values, that is the data, will actually gets randomly split into two sets. One called the training set. Okay, so
Oh, okay, okay,
let's say you have 100% of data. Okay, so what they will do is
okay,
about 70% will be used for training.
okay, okay.
Yeah, then the remaining 30% will be used during testing.
So that means you choose a grouping of data for
Yes,
training purpose and testing purpose, correct? So you
yes,
make
yes.
two sets.
Yes, make two sets. Yeah, correct.
Okay.
Yeah.
So the training supposed to be higher level because you need more to learn. Then when you test it with the other data which is reserved, it will behave properly. Am I correct?
Correct. It's supposed to, yeah,
Yeah.
supposed to behave well. Yeah.
Yes.
Sometimes they even
Okay.
use, if the data set has lot of variation, they will even use 80% for training, then only use
Understood.
20% for,
Understood.
yeah.
Understood. Understood.
So yeah, so this is the, yeah,
So
this,
you are not doing random sampling. You are doing a clustered sampling. You are choosing the whole group.
yes, yes,
I'm
correct.
talking statistics. Okay.
Yes, yes, yes.
Okay.
So the reason why I mentioned the word random is because okay, the after after you break it into a training set, inside that training set they will draw random samples during the training process.
Agreed. Agreed.
Yeah,
Agreed. Agreed. Agreed.
yeah, yeah.
But that training set is not chosen by any network or anything. It is still done manually, correct?
Correct, correct. Yes, that is correct. Yeah.
So that is done by human neuron.
Yeah, human neuron. But some people, to try to automate everything, they will even go to the extent of, just taking a random 70% from here and random the remaining to 30% use in testing. Yeah, they can do also, as long as the data set is very
No,
big.
that is no, no. When you are choosing certain data sets for training,
Mhm.
we are really indirectly going into the field called operation research. That means you are trying to see which can give you the proper logistics of, for example, there is a flight to be fueled. Where is the points where they can fuel in the world map? Where he is now? So many attributes are there. But in that, the person is choosing in such a way that he can give the expected outcome. That's all, right?
Yes.
Yeah. So the sigma value is perfect. If you come into the Six Sigma, single sigma, three sigma, Six Sigma value, the quality improvement same, right? The defect supposed to be less. Am I correct?
Mm.
So I'm trying to take you into another level. Okay, go ahead,
Okay.
please.
Okay,
we
sure,
used to call it in project management. We do similar thing: forward passing, backward passing. Then we do we use a likely value, optimistic value, less
Mm.
likely value, things like that. We do a calculation. There is a formula for that also. O minus 3 sigma, then minus n, something like that. So we do that to find out the task and likely to happen. That's what we want to do.
Okay, okay, sure.
That
Yeah,
I will share it with you later about project management. Yeah.
yeah. Sure, sure, sure. Yeah, yeah, yeah. Let's just yeah have discussions. I
It's
mean, yeah,
similar.
yeah, yeah. Good, good.
But
Yeah.
bird diagram also got forward pass. They also got backward pass to
Oh.
find the critical path method. We call it CPM, critical
Hmm.
path method. Yeah.
Okay. Okay.
Okay. Okay.
Yeah. Okay. So now I will go into the details of training. Okay, which is the most important step in neural network development. Okay, so I think we were here. So training. So the first step in training is called forward pass. Okay, so let's say now, so like I said, the training is a iterative process. So that means there will be a forward pass, that is the first step in the iteration. Then there will be something called gradient back propagation, which is the second step in the iteration. Then after that, we will check for some stopping criteria for this iteration. So should we stop the iteration or should we go on? Okay, so these are the basic the steps in this iteration. Okay, so what is the forward pass? So now initially let's say the network is not trained. Okay, so if we look at this diagram, these are the inputs, the features. Okay, then if you see, actually the previous slide you saw B, right? The bias is it's actually this weight actually. So um, they, they usually consider this input here as being 1. So 1 multiplies bias is equal to bias. So that's why it adds in that equation that you saw. Okay, but for now you can just ignore this bias parts. Okay, yeah, they have a very technical reason for being there. Okay, yeah, if I tell now, it will just be more confusing. Okay, so let's just look at this inputs. We have some
Can I summarize that the bias is any value which is out of range or it is going to skew the value, you will remove it, right?
no, it's not like that, because the input is always 1. So it is not actually coming from the the data itself. So
Oh, okay.
yeah, yeah. Actually, this is the reason for this is, if we during classification, there is something called like a decision boundary, and then you can shift the decision boundary using these bias values. So
Oh,
yeah, yeah. So the decision
okay.
boundary is
You please go ahead. Go ahead. Go ahead. That's one deep subject.
okay.
Yeah.
Yeah, it is deep. Yeah, it is that. Yeah, just quickly, the decision boundary is just some boundary separating the classes actually. Yeah.
Okay.
So
Okay.
okay. Yeah. So it is yeah, a bit advanced concept. Anyway, so these are the inputs. This is the first layer, and inside this layer we have some neurons, and these lines are the weights, the interconnections, and then you have the output neuron here. Okay, just output. So single layer neural network. Okay, so yeah, so now so initially these weights are not trained. So if you don't train, what do you do? Initially you just randomly initialize them. Okay, so this W values is the numeric value. You initialize it close to 0. Okay, you randomly initialize close to 0. Okay, then you choose a training sample, that is this value. So like we saw in the table, right? every person, I think there were 6 people in that table. So every person has some 5 attributes and 1 target value. So this x1, x2, x3, x4, x5, that will be the input, one person's input. Okay, and that will be the attributes inputs, and the output will be the target value. Okay, which we will compare with. Okay, then what happens? Perform matrix multiplication and compute prediction. So okay, sorry, here just imagine there are okay, let's just use one neuron. Okay, one output neuron. If it is 1, if it is high, it gives a high value, then you think of it as being high risk. If it gives a low value, you just think of it as being a low risk thing. Okay, low risk. So you have some inputs, go through the network. If you give if the network gives a high value, then you say it's a high risk, this person is a high risk person. If you give if you give another set of input which is for low risk, then it goes through. If it gives a low value, then you know it's a low risk. Okay, so during this process, what happens is you do this, multiply this input with this matrix. I told in the previously that these weights are put into a sort of matrix when we consider many neurons, and then it's multiplied to these inputs, right? Then we do the similar thing for this layer. So you take this output coming from this neuron as the input, and then you multiply to these weights, and then you will get a output for this neuron. Okay, so this is called a forward pass. So you're passing the input in a forward direction to the output. Okay, so that's why it's called a forward pass. So what will happen is, because these weights are not trained, that means the weights are not the correct values, because initially they have been, randomly been assigned. What will happen is your output, the predicted output will not be same as the target value. It will not be the same. So for a high risk person, sometimes it will give a 0. For a low risk person, it will sometimes give a high value. So that means your network is not trained, the weights are not optimally set, and that's why the problem comes. Okay, so then we have to supervise the training process through ground truth or target, so that we can correct the network each time it makes a mistake. Okay, so this is why it's called supervised learning. So that means you're going to use the target and try to tell the network to do some corrections, which means to change its weight values. Okay, now we'll go into loss. So loss function is to evaluate the goodness of our prediction. Okay, so I was saying, right, we want to quantify this, how much deviation is happening between this between the predicted output and the expected output, which is also called this ground truth. Okay, target, ground truth, expected output, yeah, these are all the same things. Okay, then we have this loss, okay, called mean squared loss. Okay, actually there are many losses you can design. Okay, but losses have to have certain properties. Okay, that's important. And for this case, the simple case, let's just use this mean squared error. Okay, what is mean squared error? Okay, it's very simple. Basically, this y is the target, okay, or the expected output. Okay, then this y hat, if you see here, is the predicted output. Okay, so that is the output coming from the neural network. So you take the difference and then you square it. So so you take the difference, means it's like a deviation. If they are the same, you'll get 0 deviation, right? Like 1 minus 1, 0. 0 minus 0, you'll get 0. So that is why it's called loss. If there is a lot of deviation for different, this I represents the sample. Okay, the sample number. That is, in the training set, we have m samples, and for every sample you do a prediction and you compare with the target value, and you take the difference. If they are different, then positive or negative, the square will, disregard that. Okay, that's why we have a square. Then there is a deviation, and then you sum it up, so it tells the total error. Okay, so for the entire training data set, what is the total error? Okay, if we do this.
So it is like statistically, it's equivalent to the concept of variance, right?
Yes, correct.
Okay.
Yeah. So yeah, we want to have zero variance with respect to target. Yeah, which is not always possible. So we want to have very low variance kind of thing.
Okay.
Yeah. Okay.
Because this
So,
formula looked very familiar, so that is why I asked.
Yeah, you must have seen this. Yeah, it is
Yeah.
very popular
Yeah.
to quantify. Yeah.
Okay.
Peterson, he is not strong in other subjects, but Max very strong.
Okay. Then he should,
not like that.
he should know this. Yeah. Okay. So then, okay, it is going to get a bit complicated now, because we are not only just going to compute the loss, we want to make correction, right? So what we are going to do is we are going to calculate the gradient. Okay, I'll tell you why we are going to do it, but let me just tell you. So this is the loss, and okay, for 1 minute, let's not put the actual values into the prediction. Okay, so the prediction is like computed like this. Okay, if you go back here, forward pass, what actually happens is this W1 represents the weights for this layer. Okay, first layer. Those weights multiply this vector X, then you add this bias thingy, bias thing, you don't need it, just forget it for now. Then that is Z1, it's a vector. Okay, the vector of outputs from this neuron, from these 4 neurons. So this is a 4x1 vector. Then you take that Z, you go through the activation function sigma, okay, that we talked about, because you have only done the dot product. Then you want to squeeze the values between 0 and 1. Then to do that, you do the sigma. Okay, you take sigma of this, then you get this. Again, it is also 4x1. Okay, this is also 4x1 because it's an element wise operation. So it's 4x1. Okay, 4x1 output values. Then you feed this into the second weight matrix. The second weight matrix is over here. Okay, so you feed into this, then you multiply, and then you get the output. Not the output, you have to go through the activation function, and then you will get this output. Okay, that is the A2 output from this neuron. So that is your Y. Okay, so now what I have written here is I have just, it's a composition. If you see, it's a function composition. So I have just written it in one line. Okay, so I have put this A2, I mean, like, how do I say it? Z1, this is the expanded form. I put it into here. So that is the Z1 part here. Okay, and then A1, I have multiplied to W2. So this W2, after going through the sigma, it multiplies W2. Okay, after going through the sigma, it multiplies W2. Then after that, you take a sigma of this Z. So I take a sigma of this. Then that is the final. That is the final Y. Okay, so it is just function composition. Okay, this goes in here, this goes in here, this goes in here. Yeah, something like that. Okay, so you can write this in one line. Now what we do is we put this entire function into this. Okay, let's put this into this. So what happens is this loss function is now a function of W values. Okay, so W values are the weights, right? And this is a matrix, so that means the weight, individual weight values are inside this matrix. Okay, So so that's why this J is a function of W. Okay, that's why it's a function of W. They have written it like function of W. So this, which is the W here. Okay, so you can use this to compute the numerical value of loss, and you can write an analytical formula by just plugging this into here, yeah, into this. Okay, and the reason why we do this analytical formula will become clearer in the next slide. Okay, so loss function is a function of all the weights from all the layers. Okay, so layer 1, layer 2, okay, all. So then it becomes a multivariable function. Okay, yeah, multivariable because W, there are many W's, right, which are distinct W values. So they are different variables. So it's multivariable. Okay. So initially during the first few iterations, the loss will be high as the weights have not learned the different aspects or representations of the input data that correspond to a particular class of output. Okay. So I just mentioned this previously. Okay. Okay. So now we come to the second step. Okay, so this is where the learning part actually happens. Okay, what is learning, where it actually happens. So the learning happens through this process called gradient backpropagation. Okay, so what is this gradient backpropagation? So now we have a loss function, right? So we have a loss function, and it is telling how much deviation is there from the from the target values. Okay, can we so instead of thinking it as numbers, now I put in variables. I just expand it like this. Then you have a function that that can be drawn out. Okay, for example, like this. Okay, so this is a two variable, two weights, W1 and W2. Okay, this is not a matrix. Please note, this is just a number. Okay, W1, W2. Okay, but when you say matrix, it will be a very high, kind of high dimensional function. Okay, this is 1 2-dimensional function. Okay, because the third dimension is the JW. Okay, it is the loss, the height is the loss, but the W is the weights. Okay, so when you have this kind of a matrix, for example, like this, how many parameters will be here? You have how many neurons? 1 2 3 4, and each neuron is connected to 3 inputs. So 4 times 3 12. There will be 12 weights coming from this layer, and then here there is 1 2 3 4. So 12 plus 4, it will be 16 weights. Okay, so here this function will be a 16-dimensional function. Okay, we cannot
17, no? Yeah.
Oh, including the loss. Okay,
Yeah.
including the loss. Okay, yeah, then it's a 17-dimensional function, which we cannot visualize by our eye. Okay, so that's why I just for easier this comprehension, I have just put it as 2-dimensional. Okay, W1 and W2. Okay, just think there are only 2 weights for now. So this loss function, if you just look at the function itself, you can see at certain points the loss is a high value. Okay, here it is high, here it is relatively high, here is quite low, here is low, this point also it's quite low. But if you see right in the center here, right, it is the least loss that you will get. Correct? It is so this is a loss function, and we want to minimize the loss. And what is the weight that you have to choose in order to minimize this loss? Okay, that is the whole idea. So this actually, the plotted function is actually this function. So what I did was, what is there in the picture is, it's a plot of the loss versus the weights, all these weights. Okay, so if you plot out, you might get something like this. This is not necessarily how it will look, because I have shown another picture of another loss. The loss could also look like this. This loss highly depends on your neural network structure. Okay, if you have many neurons, you can make the shape more complicated also. Okay, so yeah, so this is the loss. This is also called the loss surface. Okay, the loss function also called the loss surface. So basically what we want is, we want to minimize the loss, and what is the weight value such that the loss, which is the z-axis, is the lowest. Okay, so if we take this graph, for example, the lowest point of the z-axis, the loss axis in this graph is somewhere here, right? It's in the, yeah, this is like a bed sheet that is hanging or something like that. So then the lowest point will be somewhere here. So then you have to check what is that corresponding to, what weight is it corresponding to at the lowest point. Okay, then you take those values, that will minimize your loss function. So if you take those values, plug the w value inside here, then for any x that is coming from the data, your y value will be very close, the predicted y will be very close to your target value, because we know that this j of w is less, so this has to be close to this. Okay, so we can't okay, the problem is, if you have from like if you take single variable calculus, for example, what this is in single variable calculus, if the function is like a nice differentiable function, all you need to do is take the derivative, set equal to 0, and then you can find out these points, right? Because at the minimum point, the gradient of the curve will be 0. Okay, but actually the neural network functions, they are not very you cannot like analytically solve them. Okay, so because the differentiability problem will come. Okay, it is not oh no, it is differentiable, sorry, it is differentiable. Okay, but it is difficult, okay, to set it equal to 0 and then solve for each of the weights. Okay, I think it is because you cannot do it like because this is multivariable, right? Then you have to like solve some matrix like matrix solution, like capital A x equal to B or A x equal to 0, like find the null space solutions of matrix A, something like that. So actually it is a bit difficult to do it in an analytical way. So what we do is we do something called a gradient descent algorithm. Okay, so so whatever I said just now is like captured by this notation here. So you see, how can we update the weights such that the loss can be minimized? Yeah. So what this notation is saying is, W star is the optimal value of W, which is all the weights, these weights. Okay, is given by argmin, that means argument that minimizes this loss function. Okay, this loss function is given previously. Okay, here the loss function is the mean squared loss, which is a function of the predicted output. Yeah, and this, okay, note that this target is always a number. Okay, this is not not a issue. It doesn't cause any complication. It is going to be 1 or 0, like that. The complicated part is the predicted part. Okay, that is coming with all the weights and all that. Okay, so then what this notation is saying is argument of this function. Okay, which is, what is the argument of this function? W is the argument of this function. So what value of the argument minimizes this function? So that value that minimizes will be the optimal value. Okay, that is what we are looking for. Okay, so
A small doubt. Sorry for interrupting.
Yeah.
So if it is difficult to analyze, I mean, get this, the, appropriate weights in order to minimize the loss. If it is difficult to do it analytically using calculus or something, then is it done programmatically using like algorithms and stuff?
Yes, that's correct. Yeah. So,
Okay.
yeah, so there is it's also a mathematical solution, but it
Okay.
is, yeah, but it is done in a step-by-step process. Okay.
Okay. In a
So,
numerical way, more numerical way. You mean?
yes, it's more numerical
Okay.
way. Yes.
And
So,
yeah. Sorry. Yeah.
no,
Go
go
ahead.
ahead. Yeah, it's okay. Yeah, you can ask. Yeah, it's okay.